Good afternoon, guys. I hope you're all doing as well as to be expected. You've made it through the first chunk of exams, got to half term. I hope you can have a week of resetting yourself and then getting on top of the exams that you have coming after the half term break, which of course is all three of the chemistry A-level papers. So the questions that I've done recently on sort of transition metals and electropotentials have seemed quite popular, so I've chosen today to have a look at this question, which is all about catalysis, but it also builds in some electrochemical cell stuff as well, in terms of how we can use electrode potential data to prove that something can act as a catalyst in a reaction. So the first part brings in a little bit of alkanes as well, thinking about heterogeneous catalysis, which occurs when we crack alkanes via catalytic cracking. Then we've got autocatalysis, which is sort of your longer answer where we've got to give some meanings, we've got to explain the reaction being slow, then explain why it goes more quickly and use equations, and then using our electrochemical cell data on the back. So let's break it down, starting with part A. So the zeolites are the heterogeneous catalyst that are used in the catalytic cracking of alkanes. We have to write a specific equation to show how tetradecane, C14H30, can be cracked to form octane and a cycloalkane. So we can work out what octane's formula would be, octagon C8H18, and then figure out what atoms we've got left for our cycloalkane, which should have the general formula CnH2n. And then we've got to state the meaning of the term heterogeneous. So let's do that first. So for the equation, C14H30 is our longer chain alkane, less useful. Octane is the main component in petrol, I believe. C8H18 following the CnH2n plus 2 rule, and then we've got 6 carbons and 12 hydrogens left, so plus C6H12. Lovely jubbly. In terms of the meaning of the term heterogeneous, it's about the state or phase, which is a fancier word for state, but you will see it on the mark schemes for different types of catalysts, where the catalyst is in a different state or phase to the reactant, and that's all we'd need to put. So the catalyst is in a different phase to the reactants. And the most common combination of catalyst and reactants in terms of those different phases is having a solid catalyst with gaseous reactants. And from a transition metal exclusive point of view, the example for that would be the Haber process is one of them. We can also think about the vanadium oxide being used in the contact process as another example as well. Another well, it is a transition metal, but it's not within that topic. Another example would be our catalytic converters, using platinum to convert the more harmful gases into slightly less harmful gases, which then pass out of the exhaust. Okay, next up, we have got a student who wants to determine the concentration of ethane dioate ions, which are the C2042-, in an acidified solution by titration with the potassium manganate solution, so the MnO4- ions. The mixture is warmed before the addition of the potassium manganate solution because the reaction is slow at first. When more potassium manganate solution is added, the mixture goes colourless quickly due to the presence of an autocatalyst. So we've got to state the meaning of that term, and an autocatalyst is where one of the products in the reaction, once made, will then catalyse the reaction. So that explains why it's going to be in part slow at the start, because we don't have any of the product at the start. But as soon as we then start to make it, it will then speed the reaction up, and we need to be aware of how that happens and be able to explain using equations where appropriate, of which there are two, why the reaction is slow at first and then goes quickly. Another reason why it's slow at first is we've got two negatively charged ions trying to react with each other. They're going to repel each other, so we're going to have to put a lot of energy in to overcome that repulsion, so we're going to have a high activation energy. And I think I've already scored 4 of the marks, and then the 2 final ones will be for the equations. So first of all, explain the meaning of the term autocatalyst. So an autocatalyst is when that's not very well worded, I apologise, is when a product of the reaction will itself then catalyse the reaction. So that's the first bit done, and when you have got a few different things that you need to do, it might just be worth ticking off when you've done each part. Obviously in the first question there was only 2 parts, but here we've got to do that and then give equations, explain why the reaction is slow at first and then goes quickly. So there are a few more things for us to do here, so it may be that you find it helpful to kind of tick off as you go. You might not, and that's of course absolutely fine if you don't. So why is the reaction slow at first? The reaction is slow at first because the 2 negatively charged ions will repel one another, resulting in a high activation energy. However, once the autocatalyst starts being produced, and we do need to know for this specific example what the autocatalyst is, and it's the Mn2 plus ions. I'm going to make that clear at this point. However, once the autocatalyst starts being produced, the Mn2 plus ions, the reaction speeds up because the positively charged Mn2 plus ions can more easily react with the MnO4 minus ion. And that's the ion that gets picked off first. So we form the autocatalyst, which is our Mn2 plus, and that will then react with the MnO4 minus, so a positive ion reacting with a negative ion, which is going to bring the activation energy down a lot. That will then give us an intermediate manganese species, which is Mn3 plus, and then that Mn3 plus intermediate ion will then react with the second positive ion, which is the C2O42 minus, which will reform almost all of the Mn2 plus and see the C2O42 minus become CO2. So we've now got to show equations for how exactly that works. Now, there are a lot of equations that you will have heard me say, don't rote learn. These are ones that I would probably suggest that you do rote learn because they are a bit fiddly. However, what I want to show you here is how I actually, if you said, right, okay, show me that you know them off by heart right now, I couldn't do that. But what I can do is I can go, right, I know in the first equation, the MnO4 minus is what reacts with the Mn2 plus, and I know that that's going to form Mn3 plus as the intermediate. And then I know in the second equation that the Mn3 plus intermediate ions react with the C2O4 2 minus ions, and that's going to form CO2 and reform some Mn2 plus ions as well. And from there, I've got a really good starting point with which I can then build in everything else. Now, with these equations, the manganese in the first one is being both reduced and oxidized, so I don't need to label the oxidation states of these, +2 and +3. The oxidation state of the manganese in MnO4 minus is +7. So what we can then do, if you don't know these off by heart, is then break these down into half equations and say, right, well, MnO4 minus going to Mn3 plus would be one of your half equations, and then it would be Mn2 plus going to Mn3 plus, which would be your other half equation, and then we can join those together. So Mn2 plus to Mn3 plus, we're going to lose one electron. If we go from MnO4 minus to Mn3 plus, we're going to need four oxygens to be added onto the right hand side to balance the O's. We're then going to need 8 H pluses to be added on the left hand side to balance out the hydrogens. And in terms of electrons going from MnO4 minus to Mn3 plus, we're going to have a charge here of +7 going down to +3, so that's going to be needing to gain 4 electrons, but the Mn2 plus only lost 1, so we're then going to need to times the Mn equation by 4 to make sure that we lose 4 electrons in the oxidation process that can then be gained by the MnO4 minus. And that would be my first equation. Now you could write out both half equations rather than doing what I've just done and try and do all of it together. But as I said, I'd probably just rote learn that equation. But then if you know that catalysts can't be used up overall in a reaction, and that we can't have intermediate species in our overall equation, which by the way is this one here, so we can see that we've done it right at the end by checking they combine together to give us this, then you know that the Mn3 plus is going to have to then be used up in this stage. And I've totally labelled that wrong. My apologies. Let me get rid of that 4. The reason why I have done that wrong is because yes, I would make 4 Mn3 plus from the 4 Mn2 plus, but I forgot to add in that one there as well. My sincere apologies. And that's why, again, I would always recommend writing out the half equations, writing them out multiplied up, then joining them together, because it's very easy to do, as I just proved. Okay, carrying on. So in this half equation, the Mn3 plus needs to go back to Mn2 plus, and it's going to do that by gaining 1 electron. The C2O4 2 minus is going to become CO2, and if I start by balancing the carbons like so, that also then balances my oxygens. So I've got 2 minus charge here, and I've got no charge here, so I'd have 2 electrons being lost in that oxidation half equation, 1 electron being gained. So I'm going to need 2 Mn3 plus to gain the 2 electrons that the C2O4 2 minus has lost. And that would be then my second equation, which shows how the autocatalyst works, because the autocatalyst changes its oxidation state, which of course transition metals can do with their variable oxidation states, shown very nicely here with the +7 there too. And then we can turn the Mn3 plus back to Mn2 plus, and that shows that the Mn2 plus is acting as a catalyst and nothing else. Now, I said that the intermediate species can't be present in the overall equation, and they're not. But how does that then work? Because I've made 5 of these Mn3 plus in step 1 and I only use up 2 of them in the second step. Well, like when we join together half equations, we've got to get the electrons the same. We have to have the intermediate ions the same as well. So what we would do is times this top equation, everything by 2, 2 MnO4 minus, 8 Mn2 plus, 16 H plus, giving us 10 of the Mn3 plus and 8 H2O. And then we would need to multiply everything in this second equation by 5, so that we then get 10 Mn3 plus, which cancels with these 10 Mn3 plus. 5 C2O4 2 minus will become 10 CO2, and then 10 Mn2 plus. Now we had 8 Mn2 plus here and 10 here. Now if it's a catalyst, it should completely cancel, but of course this is a unique example because it is a product. It's an auto catalyst. So 8 here, 10 here will cancel to give us 2 on the product side. Ta-da. I'd rote learn them, or certainly rote learn them to an extent. I know that I can put them together from the knowledge that I wrote down in blue. So if you don't want to rely on rote learning them, figure out what you can whittle it down to before you can then put the rest of it together. But those are the equations that we need to show how the Mn2 plus acts as an autocatalyst. Okay, and then the final example for this question is using electropotential data for the reaction between the peroxide disulfate ions and the iodide ions. So the peroxide disulfate ions are the S2O8 2 minus, and of course iodide ions I minus. And it's telling us that they can be, or the reaction between those can be catalysed by CO2 plus ions. Now the specific example that they want you to be aware of for this reaction is actually iron 2 plus, but cobalt 2 plus also clearly works. We have to show how and why it does work using the data. It works in a really similar vein to the autocatalysis example because we've got 2 negatively charged ions trying to react with each other. There will be repulsion, high activation energy. So using a positive transition metal ion is great because then a positive will attract a negative. This can then produce an intermediate species, which is going to be the cobalt 3 plus ion, which can then react with the second negative ion to give us our products, and all the intermediate and the catalyst will cancel from the half equations to give us our overall. Now in terms of how this works using cobalt in terms of the electropotential data we've been given, I would approach this exactly like I would approach an electrode potentials question. Is I would find where the peroxide disulfate ions are, which is here, and I would find where my iodide ions are, which is there. And why have I chosen those? Because those are my 2 reactant ions. Now, based on which side of these half equations they are, the S2O8 2 minus ions need to undergo reduction, move in that direction, whereas the iodide ions need to be oxidised and therefore move in the backwards direction. Now, it's asking us to suggest how the CO2 plus will catalyse this reaction. So the CO2 plus is on the right-hand side of that half equation, which suggests that that wants to, in the first reaction, undergo oxidation. And that means that the CO2 plus ions can react with the S2O8 2 minus ions because this number 1.82 is less positive than the 2.01, so this will undergo reduction and this will undergo oxidation. So that works. That is a legitimate reaction. We've got a positive EMF, and in terms of how we explain that, that's where our inequalities come in. We would say that the the E0 value for this half cell is more positive than the E0 value for this half cell. So the cobalt 2 plus ions will be oxidised, and in the process will reduce the S2O8 2 minus ions to SO4 2 minus. And I will write that in a second. The intermediate that we've then made is these CO3 plus ions, and if we then look at where they are in relation to where the iodide ions are, this is where transition metals are so brilliant at being catalysts like this, because we can now have, for the second reaction, the CO3 plus ions being reduced back to the CO2 plus, which obviously then means that will cancel out of our 2 equations for our overall. That will undergo reduction now, and the iodide ions needing to be oxidised, well, that works again in terms of the numbers, because 1.82 is more positive, that's where reduction will want to occur. 0.54 is less positive, so that's where our oxidation will occur. So again, the iodide ions can be oxidised as the CO3 plus ions are reduced. And that's what we need to say. And some sort of indication that we are sort of transitioning between these different oxidation states of cobalt will be important as well. So I'm going to write here CO2 plus can become CO3 plus and then return back to being CO2 plus, and that's important because that's how we know it's being a catalyst and not getting involved in the reaction. It's reformed without being chemically changed permanently overall. Okay, now I'm going to use my inequalities. So for the first reaction, we had the S2O8 2 minus and SO4 2 minus E0 value being greater than the E0 value for the cobalt 3 plus, cobalt 2 plus half equation. Therefore, the CO2 plus ions will reduce the S2O8 2 minus ions to SO4 2 minus ions and will themselves be oxidised. And that's our second mark. The first is for the idea of the cobalt being able to transition between the +2 and +3 oxidation states, and then you get 1 mark for both the inequality and this statement here. And then we're going to get our third mark then for the inequality for the next reaction and a sentence as to what that means. So then we can say that the E0 value for the cobalt 3 plus, cobalt 2 plus halves equation is then more positive than the E0 value for the I2 I minus half equation. Therefore, the CO3 plus ions will oxidize the I minus ions to I2 and will themselves be reduced. Now that's 11 marks, and I know it's all about catalysis, but they have brought in different aspects of it, which hopefully would mean that if this was something they decided to replicate in the papers next month, that you would be able to pick up some of the marks for one of the questions on here. I would say certainly part A is the easiest one. I think with part B, you're probably going to be likely to be able to remember this first part, but maybe not the equations. But give it your best shot to rote learn them. And then with this one, I think it's knowing how to manipulate the table of data and then what is necessary in the answer. So because we're thinking about catalysts, changing the oxidation state is important, and then it kind of becomes an electrochemical cells question. And if anybody needs any help with this or the autocatalysis or any other questions, as always guys, please just let me know. I know it's not going to be a very fun half term for you, but I hope that you can take a little bit of time to rest if you've had exams so far, and that you can then get back on the horse, as it were, and smash out some revision for the upcoming exams. Sending all my best wishes, and I will catch you soon. Thanks for watching, everyone.